Okay, we're live. I'm about to tell you something insane. Let me just post my promotion. Hey, look. YouTube.
Stream. I spent the entire thing basically solving two problems.
All right, cool. I believe we're live. Let's just make sure here. That looks live to me. Let me click on it. Click. Hello, hello. I hope y'all can hear me.
Today's day 3 of learning rock.
Yeah, so cool. Let's get to it. Thinking out loud, okay? Yesterday, I mean, I kind of talked about it in my little video there. I mean, man, what a context window we've been building here. And you know, where I've actually found my understanding in these areas is kind of just like up in the air. I'm not sure where exactly, you know, I can say that was the part I understood. Unless, you know, you're very, like I said, you're very proactive about using GPTs. I think it's ridiculously helpful. Don't get me wrong. Like, the LLMs are ridiculously cool and they're helping me out. And I'm finding the information that I need to understand it probably at a faster rate than, you know, doing it otherwise, like, I mean, pre-LLM phase. Like, I'm able to just like literally get on here and kind of have something in a tutor capacity. So that's kind of interesting. I feel like sorry, I was distracted. I feel like it kind of gets lost. Like, you know, say for instance, like I'm up here, how to solve acceleration material derivative. This is, or you know what, that's a bad example. Let's see something. I ask how is velocity calculated, and for something, this is what made sense to me the day before. And then, you know, you continue on, and I understand it kind of gets like, how do I say? There's not really a highlight option or nothing. That's okay. You keep on asking it questions. You keep on asking it questions. Then instead of like getting back to that section, which is kind of long, as you can see, it's very like, where is that? We can do a Control F and like look through all my 119 instances of velocity. You can find out, you can't really like, you'd rather just be like, what is velocity again? Because then you don't have to scroll up and down everywhere through any of that. So when it does that, maybe the GPT hallucinates. It doesn't give you the same thing that clicked last that it does now. Matter of fact, you didn't even specify unless you were like very strategic about your understanding of it. Unless you were very strategic about being like, that is the part that made sense to me. Make sure to hardwire that into your context window or into your memory of our conversation. It's not really serving much. So here's the thing, and then you might be a great note taker. You're gonna highlight that. You're gonna throw it in the side. That's the part I understood. Now, when you look back at it, you're gonna still have all of this, you know. Man, what? Like, I don't know. You can kind of maybe go on. You can keep on doing this kind of thing or get organized about it, but I think something needs to be done about that. So, anyways, well, we will continue using it in the learning capacity because I really do wanna work on it. Matter of fact, you know, I have, obviously I am working on it, but I intend to do some real things about it. So, anyways, here's a crazy thing. Yesterday, somebody in my TikTok comments randomly said, "Hey man, you should, whenever you're learning about fluid mechanics, go ahead and do yourself a favor and get good at this right here." Okay, and now recall yesterday in the equation, that's not what I'm looking for. Right here. When it had me calculate the dynamic, what did it ask here? It had me calculate basically income. Let me just make sure that I'm getting this right in this moment. Continuity, basically, of these components right here, right? And it led me down this this whole thing where I was learning about cylindrical or circular cylindrical coordinates, right? Which is a different. I mean, here we'll pull up the. It's kind of where the three values, instead of Vx and Y, it's R, theta, and Z. And so I didn't know that. I had to kind of like derive it on the spot here. And some guy in my TikTok comment says, "Hey dude, get good at the math behind this. There's something called the Navier-Stokes equations." And I looked at them, and I was like looking at some of this stuff. Continuity is what we used yesterday, but I was like, wait, that's exactly what I needed the entire time. I was ripping my head off just trying to get better understanding of that. Or matter of fact, hey, I ended up deriving it, more or less, yesterday. Not realizing that there's like a whole, you know, it's important what we have right here. So today, let's do ourselves a favor. Let's take a step back and let's really get a good understanding of that before we hit any of these right here. So, because I mean, it's about to get pretty difficult here. And then tomorrow we might, hopefully, I'll probably try to work on the rest of this tomorrow. But then we can maybe dabble in something else. Because another message that I got was just like, all right, which tangibly, there's so many parts of a rocket, which part do you actually care about? I said, I don't know. Because so basically the two options here are, here, let's do the nose tip. The nose cone of rocket. It's the most, so I mean, what does it say here? It's a conically shaped forwardmost section of a rocket, guided missile, or an aircraft. Okay, I need it for the rocket, but basically there's a way of simulating this through a company called Open Rocket, I believe, or a simulator called Open Rocket. Here we go, where you can build everything you need to design, simulate, and fly better rockets. So it sounds pretty insane. So, you know, we're some food for thought, basically. Some food for thought. So we're gonna go back here and let's understand what these Navier-Stokes equations are. Yeah, so maybe I worded it incorrectly. I don't think I derived, but it was like throwing me. It was throwing. I mean, right here. This is basically. I believe that is the top part of the Navier-Stokes equations, like the continuity part. Right here we have continuity. Does that look pretty aligned? I'm pretty sure it does. Times year 1 over r. Okay, so that is kind of interesting. I thought it was. Let me just see if I understand this correctly. Okay, no, I was just wondering if no, let's not take it a step backwards. Let's just get our footing right. So my man right here. Let's go to NASA. Let's figure it out. No, not helpful. We can ask the GPTs. We can also maybe just hop on here. I need something text-based. I'm also trying to just get good at that skill. You can watch videos. They're very fun, but maybe actually. No, let's stick to text because I do want to. I'm trying to highlight also how we can use the LLM. So how best to do that then? This. So maybe we'll go. So I mean, one of my favorite resources is here, where it's like. Making public policy. Okay. Hydro. Blah 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 blah. Nope. I don't want to use Wikipedia because it's gonna. Possibly. Sometimes Reddit does have some gold. So maybe this might help right here. It's a partial differential equation. Differential equations describe how the inputs affect the outputs of a function as they change. Yes. One common intuitive one is common representation. I got a funny message here. let's continue. Let's find as mass times velocity if the mass. I didn't mean to flip you guys off. I was just straightening my things. I think this is my. Somebody's saying, "This is your thinking position." Yes, it is. Okay, it helps me. I don't know. Maybe it's a rhombism. Okay, come on. We just defined. Jesus, I like that I just said that, because that just brought me out of my slump right there. Because I was like, this is like mechanics that I've learned way back when, but obviously I don't have much command over it now, but define as mass times velocity. Okay, let me sharpen up. P here is momentum, which is defined as mass times velocity. Fine, good. If the mass is unchanging, this can be simplified to m times dv or dt, because m becomes constant. I understand this. Or ma. Oh, that's kind of sick, because dv. Okay, fire. I like this, Mr. All right. It's interesting to note that the original form is used where mass changes are significant. The original form is used where mass changes are significant, like rocketry. Interesting. I like that. Anyways, if the differential equation is linear, then finding a solution is possible. So finding a solution is possible. External force. Invert the equation. It means if the differential equation, is linear, then finding a solution is possible given an initial position and velocity and plugging in the. I'm going to figure out the net external force. We can invert the equation to calculate the acceleration based on applied force. Over my head. We can solve the differential equation for a closed form. No siree. I'm not gonna give up though, come on. Navier-Stokes is non-linear, so no okay, wait, I understand. If just, I thought it was, the differential equation I thought they were talking about was the linear. Right here was the Navier-Stokes, but just some differential equation is linear, then finding a solution just is possible. Given an initial position, velocity, and plugging in the acceleration, the net external force. You've got this. Thanks, Fareed. I appreciate that, bro. So this is kind of flying over my head here, so I'm gonna do what I've been doing these streams and prompt to myself healthily. Can you please explain this to me like I'm a beginner? Beginner. I understand this. Good. Good and good. Let me also pull up my notes. Let me get on my iPad and my little stick. My little I can't find it, but we'll just use pen and paper. We'll go all natural. My friend told me that I should start doing like a hand cam. Like I should start maybe showing the math. This is kind of like the math from yesterday's video, but I'm just recording off my Mac, so here we go. Velocity supposition. I understand that. Well, linear means here linear differential equation is one word. Simple direct way, not multiplier. I understand this. I understand that. I understand that we can find a solution to linear differential equations. Example, the falling ball. Okay. Differential form. Hey, Rylan, my man. Let's go. Let's go. I'm learning the Navier-Stokes equations right here. I don't think it's that interesting, but I'm trying to get my foundations right. No, sir. Bro, let me show you something. This is my, I mean, I kind of showed this in my video, but this is the state of my journey right now. I mean, like, it's this and notes, but like, it was literally just crashing on me all of yesterday. But no, I'm just trying to get those foundations right, buddy. And that's fire. Got 3 viewers. Damn, bro. I think I got some motion. I know. I know. So right here, differential forms. Acceleration is equal to gravity. Okay, we can integrate this to get a closed form regular equation. So integrating is a step up. Got it. That's a solution. A direct formula for position over time. And what is it trying to form? Okay, that you just can't find a solution. Okay, I understood that. Understood that. Differential. I understand all this. You like. So then the second part, where's my Reddit post? The Navier-Stokes is nonlinear and no closed form is known. Imagine a box, say a wind tunnel, just a space that has 3D coordinates. No closed form, and let's find out right here. I think you might have said it. Did it say it? Anyways, so we solve the differential equation for a closed form. Oh, right here. How things are. The state of things based on the state of the other things. No. It's a rule of change. That's a differential equation. Tells you acceleration. If you work through the math, you get a simple direct formula for where the ball is. Okay, if you integrate, I get that. This is a position formula. So a direct formula. Oh, okay. So if you're just able to integrate it a level up and get a solution, then it's a closed form. If you're able to get a solution from the direct formula, then it's a closed form solution. Whatever you get from that is a closed form solution. Okay, Navier-Stokes is nonlinear. So I think I'm having a disconnect between how this guy's trying to explain it intuitively, and I'm trying to understand it mathematically. So, and we'll try. Navier-Stokes is nonlinear. And no closed form is known. Oh, okay. Imagine a box and say, so let me get this right. Invert the equation. Apply force, we can solve the differential equations. Equation, how things are, the state of things based on the state of the other. Okay, let's just see what he says. Imagine a box and say a wind tunnel, just a space that has 3D coordinates. Its closed form were known. If a closed form were known, then predicting the wind velocity at any given point in the box, given the velocity at the edge of the box, is trivial. Plug and chug. Got it. If a closed form was known, because then you get position. Instead, we have to resort to numerical models. Split your box into tiny pieces. We have to resort to numerical split your box. Oh, they follow a volume of air through a piece to calculate a fairly good solution to the velocity at the far side of the piece. Repeat again and again through your box, and eventually you have a whole bunch of points in your box where you've got a fairly good calculated number. You can see that this is a much more complicated and intense process than just calculating one number. Let's go. Okay. I actually look forward to when I actually understand something here, because then I can come on the next day and just be like, I got an understanding. This is very intuitive. I want to see what this looks like. All mathematically, so. So we'll go down this. We just need some more explanations. I'm scared to go on the wiki, but intuition. Encyclopedia. I don't even know which source to look like. So we can We can honestly, because I'm trying to prove a point, we'll just be like, I always keep that prompt on because I don't understand otherwise what to do. Give me 1 second. I got a very kind comment here saying this is my propulsion textbook. Somebody linked their propulsion textbook, very kind. It was on my Instagram, I really appreciate that. Rocket exhaust or plasma. Interesting. Yeah, also in our doc here, we're gonna brush up on intuition. I mean, maybe not intuition is what I need. Maybe math is what I need. We'll do that in a sec. We'll just pretend like we understand. We'll just rote memorize the equations because that's kind of what my current understanding is. I just have the equations memorized. Dragging one ball, tiny piece of the fluid, its motion is. Oh, gotcha. So I understand this intuitive example. I just want to see the equations now. Don't worry about memorizing, it says. I think I do need to worry about memorizing here. Okay, so understood. Let's try this next part of the problem. I think it already has it loaded up. The only portion of the shear strain rate that could be a non-zero for this velocity field is this. Okay, thank you. Give me that. Derive u theta of r. Derive this component for which, so this is kind of free parameter. In a zero strain vortex. I'm actually kind of glad that I'm slowly kind of getting understanding of like this. Like this isn't as hard to understand. It is still very difficult, but what is the physical meaning of this parameter? For this zero strain vortex, calculate the vorticity. The zero strain vortex, calculate the vorticity. And I did remember somewhere here. Vorticity is delta by u. It's delta by u. I actually was curious about the. Oh my god, we're all the way up here. Let me get to the bottom. Is vorticity the same as calculating the what is it? Continuity part? It's gonna say I'm super dumb. Short answer, no. Okay, so I think I forgot my formulas. Oh, yeah, I'm getting a little confused here for sure. Theta times U. Gotcha. So how is vorticity calculated? I need the math. Okay. Okay, because I remember reading that this is somewhere equal to, or this can be applied to any type of this, even if it's cylindrical. Okay, I think this is like a memorization thing, but okay, well, we'll just plug that in my brain for now. I want to know intuition of this later, so maybe I'll say this. How is, what am I talking about? Understand. Oh, and by the way, I realized that this isn't in the right day. My girl said that it's shift tab. To go back? No. Okay. What is the vorticity for? Nope, that's not what I'm looking for right here. For vorticity in the X, Y, Z components. Matter of fact, we're doing that right now. That's not even good wording. Understand the intuition for vorticity components in the X, Y, Z components. Vorticity is a vector. Yes. Yeah. This all makes. I'm making it make sense. That's good. Okay, yeah, makes sense. So back to this. Simple 2D flow. Gotcha. So back to where I was. Nope. Okay, so back to the question here. Shear strain rate, which I'm pretty sure they calculated as part of the, what is it called? The, I could search it up right here. Okay, please explain. No. Problem two, please. Okay, it's still thinking. Let's get something here. So this has kind of been an issue lately. Is that so? When it vanishes, I think it just gave me the answer straight up. That's okay. Which strain is the R theta shear? Insane. Let me just also pull up this, like, Okay. The rate of deformation tensor is often written as this. So that makes sense. I was confused about what that even meant. It's a lot of big words. I'm in the wrong part. Right here. Okay, got you. Okay, yeah, makes sense. So set it to 0. I wonder where this equation's coming from. Oh, it says it right here, okay. du theta dr minus, carry that over, so just set it equal to 0, it's saying. Set it to 0, what do we calculate? Take the 1/2 out. What is ODE? Ordinary differential equation, good. Rearrange. Okay, I understand. So just after deriving, it's been a minute since I messed with omegas. Or seen an omega. Not messed with omegas, but. Yes. when there is no shear in this world. Well, for what? Yo, the stutter is insane. It's not slide past each other. No shear deformation. The same thing is when is the shear strain rate equal to 0? Understood. I understand this. Imagine several circular rings of fluid, one inside another. One inside at the inner ring. Understood. So we're looking for the swirl pattern where every ring moves as part of. So, I mean, really quickly before I move on here, I wish there was like a feature. Bang. You can just be like, this is the part I totally understood when it came to that. And, like basically just a way to like measure importance. So, some ranking or something. Because otherwise you're left with, you know, this. All of that. I'm not even going to do it. I showed it in my video. I put some Jeopardy music over it. But I would like to see the math. In cylindrical coordinates, the shear strain rate for swirl is. See, I'm wondering why they talked about some. You know what? No, let me focus. We want that to be 0. I get it. We want that. So I'm getting hyped. Sometimes you get hyped when it actually clicks. It's clicking so well. All right, let me write this down. Let me also just brush up a little bit on my deriving skills. So this, see, wait. Let me also just make sure. Is it always okay? R theta. Let me look at the document. Derive the U theta R. Get this. I'm kind of confused what this term is. They threw that on me a couple times now. That's okay though. Okay, so I mean, I understand the intuition. I'm still a little bit, my only part, okay, I don't need to prove that this is equal to this. Okay, so this is just shear strain rate. Is it always? Okay, so this is for a very specific type of strain rate. I'm trying to like picture what this looks like, so. So how to calculate vorticity with this new zero strain, zero strain vortex. What is this? Oh, wait, I know this. It's just the wait, what? Shear strain rate is calculated as just the derivative of speed over, or delta, upside down delta symbol in W. So with the new chords, you got this, I trust. Yeah, yes please. A pure swirl that only depends on over. So this is just these two components are 0. If it only depends on R, you only need to mess with this. Got it? So these first two coordinates are default 0. When it comes to the z coordinate, that's a curl and cylindrical chord specialized to got it. Plug in the 0 strain swirl. Oh, u theta. Okay, r squared, yes. Derivative of that is 2 constant r. Take out an r, 2 pi. Got it. This totally makes sense. Non-zero vorticity. Yeah. Explain that to me. Every ring completes a turn in the same time, right? Yes. Constant W pointing along the axis. Oh, okay. One tiny step. If instead of u theta is equal to potential. As opposed to what? What was the original vortex we had here? My question was no. Zero strain vortex. So an actual vortex now. What happens when you actually have a vortex with maybe some strain? Is that what it's saying by a potential vortex? Some vortex with some strain. So if there is some potential vortex, what is u theta equal to? So up here when we actually had set up the potential. Here's equal to 0. Okay. Substitute the given flow. Got it. Substitute the given flow. So here, let me try to do this by myself here. Where was our original That's not what I'm looking for. Where is the question? Okay, so if u theta is equal to u of r and u of w, right? U of w? No, u of z is equal to 0 and 0, but only u of r is equal to, or rather u theta. No, I'm getting, if u of r is equal to 0 and u of z is equal to 0, but only u of theta is equal to, man, I don't even know what that symbol is. It looks like it's just like a cutoff T. Okay, whatever, that thing. I'm guessing it just means some constant, I hope. I'll look into that in a sec. 2 pi r. I gotta get my Greeks right. Okay, if r u theta is equal to r this. Okay, so this is a constant. So wait, let me just do this again. I'm just using that for reference, but and that is because u theta is equal to u theta of r times r. Man, see, that was the entire time I was thinking that u theta is just equal to a function of using r as a variable, but it's actually literally just u theta is equal to u theta times r. I gotta get my physics brain is not is different than my, or the notation is just different. So d out of dr r u theta. So r u theta becomes, I think just like they said, some constant, because the r's cancel out, and then it's just that weird symbol that they gave me over 2 pi r, or 2 pi, so just some constant. So then I get this a constant exclamation point. So the derivative of a constant 0, got it. So everything is 0. The vorticity vector is 0 everywhere. Well, that's kind of trippy right here. The potential vortex looks like it's rotating. In the previous example, we had where it was actually rotating. It will be a single free parameter remaining in the zero strain vortex. That's what I did. And that's what we figured out, where it just is like one big, like if I'm just imagining a cup with water, that's my vortex, and it's just moving in uniform. There will be a single free parameter. What is the physical meaning of this parameter? That's just the axis in which it's like rotating in sync. So for the zero strain vortex calculator, this is just like a follow-up problem to like understand what's going on here. Would you like me to show a side-by-side sketch? The two. This vortex looks like it's rotating, but each fluid element just moves in circles without spinning about its own center. So crazy. The layers slide past each other, but the fluid parcels themselves aren't. That's why it's called air. The speed would blow up. Shear strain, no shear strain. Vorticity is constant. I think this is throwing me off, but fortunately it wasn't part of the question, which is not a good enough reason to move on, but I'm gonna move on. So I understand what they were trying to grill me on here though. So that's good. Now derive u theta r for which wz is equal to 0. I thought wz was equal to 0 previous. Oh, but it's dependent on... Oh, we just did that. Okay, cool. So I don't have the liberty of being able to forget what's going on right there. They literally just checked me. They were like, you must do it. So, and I think we already solved it right here. Funny enough. It moves in circles but doesn't spin about itself. Yeah, cool. Oh my god, my brain, bro. Yes, I would like to recap, honestly. UR is equal to that. They give you some potential setup. Got it. Let's go. Okay, let me just also get a real good look at this data. The angle component. The direction of motion at each radius stays the same. I think I'm having still a bit of difficulty understanding that from earlier. That I understand this, I understand this. Okay, that makes sense. Cool, understood. Like at a very high level, a very low level, I understand, but that's okay. Okay, I'm gonna do myself a favor, and I'm going to hold up. It's okay, we're getting there slowly but surely. We got this. I'm getting some subscribers. It's kind of huge. Thanks for subscribing, whoever is subscribing, man. Thank you. Very kind. I'm not. Like I said, I'm not the influencer type, so apologies if this isn't the most fun. But I think there's like maybe a niche where you can just be here with me and do just know that there's somebody going through it, but I'm committed, so I'm committed to getting it done, so y'all can enjoy that. Y'all can have fun. I'm just pulling up the chat here, making sure that I don't miss if anybody's trying to communicate. My friend last time was trying to communicate, so and I kept on missing his text, so I just want to make sure that is not the case. Okay, let's go back to it. Let's go. And we're gonna take a quick little detour here. We're gonna make a nice little detour here. I want to see if y'all can understand what's going on here. Now your Stokes. Why is that the thing? Oh, is it because of OBS? It's possibly because of OBS. That's okay. That's okay. Somebody just sent me their textbook. Let's see if we can do it. Philip Hill and Carl Peterson Mechanics and Thermodynamics of Propulsion. Well, looks inviting for sure. Ooh, I see a word that I like. I'm so superficial, I just see rocket and I'm like, that is exactly what I want. Kitty Hawk, North Carolina. We're moving into propulsion. That's what this detour is, but we will. I'm gonna work on that. I'm glad that because I did my two problem. Basically, last stream I was able to get through F and E. I mean F and A, and this was. I mean, looking back at some of this, like I'm like easy, but easier at least. For this though, yeah, I got through these three. I got through these two. So D and E, we're so close. I really hats off to people who have command of this. That's probably the only question that I just understood here. Could a rocket vehicle be propelled to a speed much higher than the speed at which the jet leaves the rocket nozzle. Could a rocket vehicle be propelled to a speed? Okay, got that. Could a jet or rocket engine exert thrust? Exert thrust. Well, this. Okay, got you. In theory, a jet. So. Hmm. Okay, fine. The tube. I love tubes because I've just been literally. I mean, hey yo, but I mean, I don't care. We've been trying, like, to do duct things. Like, that was the first problem, duct. So that's why I'm like, I've been understanding the tubes make sense. Tubes are kind of like my foundation right now, so that's good. Let me see this figure part A. Close to, this is, where's figure part A? Right here, okay? Cross-sectional area A. Internal pressure. Okay, wait. I'm just trying to really plant this in my head. The internal and external pressure forces in the x direction clearly balanced and no net thrust is exerted by the internal fluid or the external atmosphere. The external atmosphere. The right half of the tube is instantaneously removed. Bouncing forces applied to the tube. The instantaneous thrust is. I don't know where that comes from. Is that before a finite velocity is developed at the tube exit? Okay. After a small finite time increment, fluid instantaneously leaves the tube at exit velocity. Okay, shown as a part C. Okay, well, the internal pressure on the left and drops to P. The thrust is now this, as opposed to P0, it's some. Okay, shown as part C, while the internal pressure on the left end drops to P. Got it. Thrust is drops from P0. So P0 I think just represents, let me just see if they're, what's going on here. Okay, I didn't even realize that subscript wasn't at 0. I thought it was just, oh no, it is. No. My vision's cooked. It's A. External ambient pressure is PA. Thrust is equal to, this represents thrust. Yes, it does. T0. Got you. I wonder what plus dt means. I'm curious about that. What is t0 plus dt? Okay, so let's just see if we can go to the Jippity. Be like. Delta t. Oh, I'm thinking about derivatives, man. Delta t, change in t. Some change in t. Okay, gotcha. Very small of time later. Gotcha. Okay, I like it. Like, it's very friendly and all, but then you actually have to get into the nitty gritty and just start like cranking out problems, and then you're just like, what have I done? I don't know what it means by that. I want to see if it can pick up P0. The internal pressure on the left drops to P. Let's see if it can even. Bernoulli's principle, man. It drops to a P. Let's just, okay, I get that. It's a notation skill issue is basically what's happening here. If that drops to P, the thrust is now, instead of P minus BA. Okay, fine, got it. Internal state minus external state. Got it. Part D. At the same rate. What is steady state? Okay, I get that. I get that. I get that. Right, it's so like heartwarming when you actually get what's being talked about. Cause like you jump straight into something like this and you're just like, man, I don't even. It just throws off your understanding. But it's also like, hey, you can't get too comfortable with this feeling of just being like, oh, I'm always gonna get patted on the back. Like you're never actually gonna apply yourself, but or you could do the gradual transition, but let's go right there. Let's go straight to it. Shearing forces. Oh, what are the chances? We just talked about that. Whoa, that's kind of trippy. I just totally understood that. They illustrate the general idea. let me just get this right. In part D, sorry, it's very silent. Because I'm logging in. Here, is this the steady state thruster? Steady state thruster. Steady state thrust could be generated. Oh no, that's not the steady state thrust. This is just supplying fluid. Steady state thrust is where your thrust continues at a constant. This. Pressures are aligned and understood. And wow. Humbling. This entire thing is humbling. The internal geometry of thrusters, such as a turbojet. One second, I'm getting it. Got you. What's the difference between? Okay. Is M different than UE, or is it saying mu? Oh no. Okay. Let it talk. In which M is the rate at which mass flows out of the chamber, and UE is the mass averaged exhaust velocity. It's kind of crazy. I just realized, whenever you just like find out you know that you've been saying a word the entire time, and then you're just like, oh, so that's what it actually means. Like you actually you gain consciousness about a word. That just happened to me for exhaust. It's exhausting. Good on charge. Mm-mm. Okay, got it. Okay. That is a pretty interesting layer. There's something inside of these conditions that are already apparently tough to map out. You have to put somebody in there, so that's or something in there. Hmm. Wonder what that is. Hey. Oh shoot, we're almost at a couple hours, but we'll yeah, we'll end sharp. I think I'm actually pretty interested in what's going on right here. I'm gonna continue learning this after, but like it's cool. Yeah, I'm curious about the history for sure. I just want to see some of this, some real application. You know, I'll quickly go back to that, but another problem set somewhere. Problems, cool. Okay, that's good. Then, that being said, I think we'll call it quits for today's stream. Yeah, cool.